He kōna ipurangi tēnei nā te reo irirangi o Aotearoa.
They say life is stranger than fiction.
There's a sort of calculable probability that that would happen spontaneously, but when you work out the chances of it, it's so unlikely that it would never happen in the lifetime of the universe.
But sometimes what we see in movies or read in books is so incredible that it obviously couldn't be possible. Or could it?
If you have a watch and you try and measure the passage of time, that passage of time that you measure, the amount of time that passes depends on your state of motion.
Welcome to Sci Fi, Sci Fact. I'm Brian Crump, and this is a podcast where we take science fiction's strangest ideas, weirdest elements, most unfeasible plot drivers, and explore if they could actually happen in real life. Maybe they already have. And in every episode, we bring in a scientist from New Zealand's MacDiarmid Institute to explain the theories behind some of fiction's more fantastic flights of fancy, if any theory exists. In Tenet, it's time itself which seems to be the main plot device and manipulating time. And here to tell us whether Christopher Nolan's Tenet has any real-life equivalence is Professor Bill Williams. He is, of course, from the MacDiarmid Institute. He's a principal investigator. He's also a professor in biophysics and soft matter at Massey University.
One of these bullets is like us, travelling forwards through time. The other one's going backwards. Can you tell which is which? How about now? It's inverted. Its entropy runs backwards, so to our eyes its movement is reversed. We think it's a type of inverse radiation triggered by nuclear fission.
You didn't make it?
We don't know how yet.
So where'd it come from?
Someone's manufacturing them in the future. They're streaming back at us. Try it.
How can it move before I touch it?
From your point of view, you caught it. But from the bullet's point of view, you dropped it.
But cause comes before effect.
No, that's just the way we see time.
Well, what about free will?
That bullet wouldn't have moved if you hadn't put your hand there. Either way we run the tape, you made it happen. Don't try to understand it. Feel it.
In Tenet, it's time itself which is squishy, which you can manipulate. But I haven't seen the movie. You have. Tell me how it drives the plot, time in Tenet.
Well, that is a good question. So I would say, yeah, I enjoyed the movie, definitely as a sort of, a cinematographic experience. There's some interesting things happen in the plot with certain assumptions that are made at the beginning. And how the time travel aspect, how this sort of drives the plot is that essentially in the future, there is a method which is invented to take a material and do what's called, I think they call it inversion in the movie, which is an entirely made up thing in which the entropy of the material, so we can say something about entropy in a minute, that is something with a sound scientific foundation. But in the movie, they somehow managed to take a material and essentially manipulate it so that its entropy runs in the opposite direction. So I'll come back to a few of these points, but essentially this would mean that instead of, in the world we live in at the moment, we kind of imagine that as time progresses forward, a lot of our ideas about the perception that time's moving forward is that we see systems become more and more disordered. And we don't tend to see things spontaneously order themselves. And so if we're watching a process happen and the disorder of it increases, we tend to think, oh, that's something going forward in time.
For example, Bill, say the energy in the cosmos, with entropy, it disperses.
Yeah.
It doesn't gather together in clumps. On the whole, it disperses as the universe, as the cosmos expands, and eventually that will be evenly distributed around the cosmos, and that's why time moves in that direction.
That's exactly right. You said a very insightful thing there, which is essentially it's to do with the sharing out of energy. So often if you ask people, how they think they can tell if something might be allowed to happen in the future, which is, all about the passage of time, they may well answer with something to do with energy and say, oh, well, we can use energy to do this process. But in fact, if you think about energy as a concept, one of the first things you probably learn at school about energy is conserved. In a way, it's made up as the thing that is conserved. What that means is that the amount of energy never goes up or down, basically. So, when we have these campaigns to save energy, in a way, we don't need to save energy. Energy is the one thing that doesn't need saving because it never goes away. But what does happen is that energy flows through systems. And as it flows through systems, exactly what you said, the word we use in physics, it dissipates. So that is that energy gets more and more shared out between more and more systems. So how you can tell sort of times going forwards it's not like the energy's running out. It's that the energy the system has gets more and more and more divided until all those parts that the energy is dividing to, it's sort of just shared out among them in a way that it's very unlikely now that amount of energy can really do anything useful because it's spread around to lots of little bits of the system that don't know what the other bits are doing. And we tend to see this as disordering. So, for example, if you had a balloon which had some helium gas in, if you pop the balloon, that helium gas will leave the balloon and it will disperse and it will go and bang into other gas molecules. But it will you can imagine spreading it out over the room, exactly what you said. So ultimately, every part of the room has the same likelihood of having a helium molecule in it. That's something which we associate with things which actually happen in the universe we live in. But what we wouldn't see is we wouldn't tend to see a room that had got helium distributed in it. We wouldn't see all that helium go and get together and then, cover itself by a balloon. That's something that we wouldn't think would happen. And if we saw that happen, we would kind of go, "Oh shit! It looks like something's going backwards in time here." So that's
the only way we can do that at the moment, Bill, is for some outside force, such as a human with a pump pumping the helium into the balloon.
That's exactly right. So, in actual fact, there's a sort of calculable probability that would happen spontaneously. But when you work out the chances of it, it's so unlikely that it would never happen in the lifetime of the universe. So often when you talk with people about these kind of things, they'll go, "Oh, but it's not impossible." But, well, okay, it might not be impossible, but if it's so improbable that you'd require many, many lifetimes of the universe for it to happen, we basically use the word that it's impossible. So there's a very famous theorem in physics called the second law of thermodynamics. And essentially, this is what the second law of thermodynamics says. It says that if you take everything into account properly in a process, you will always find that processes that happen in our universe, the entropy basically always increases. That is, things get more and more disordered.
But in Tenet, what's happening is it's a material that doesn't undergo entropy.
Yeah, so the key thing really when you're talking about entropy isn't so much what the value of entropy of something actually is, it's how that value of entropy might change during a process. So the example, for example, in Tenet is one of the first things the protagonist in the story does is he kind of he thinks he's firing a bullet, but in fact what happens is a bullet kind of shoots out of the wall that it was embedded in and goes back down the barrel of the gun into the gun. So this is a process which we would say is going backwards. He's not firing the bullet, he's catching the bullet. Okay. How that would happen in reality, I have absolutely no idea. I think this is purely it's a kind of a thought experiment,
Bill, if it's possible for a material to not have entropy, why would that affect time? Doesn't everything have to lose its entropy in order for time to change? You can't sort of just change the time at one place independent of the rest of the cosmos, can you?
No, that's in one way, that's exactly right. So I would say with regard to Tenet, that's exactly right. I mean, it's important to realize that every system, you can calculate an entropy for any system. So everything sort of at a particular instant in time will have a particular entropy. But the deal is, if you imagine a process happening now, if that process changes the entropy in the way it goes up, we would say that's an allowed process. And if we saw that happening, we wouldn't think anything about it. We'd just think time was running forwards. Whereas if we calculated the change in entropy in a process and the entropy got less, if we actually saw that process, it would look to us as if time's going backwards. So let me give you an example that I think's a decent example, is if you play pool, you know that at the start of a game of pool, you have, is it 15 balls in a triangle? Maybe it's not 15, I can't remember. But you've got, you have the balls in a triangle, and you break at the beginning of the game of pool, and you scatter all the balls everywhere, right? Yeah?
Yeah.
So if you imagine now you took two pool balls, and imagine for a minute we're looking down onto a pool table, and imagine there's only 2 pool balls, and I push these pool balls together towards one another, they collide with each other, and then they bounce off, okay? And suppose I filmed that. So I'm filming the collision between just 2 billiard balls, okay? Now, if I played you that movie, and then I played you the movie backwards, if it was only 2 balls, would you be able to tell if I showed you the movie forwards or backwards?
No.
That's exactly right. You wouldn't be able to tell. So that you can't tell there if time is going forwards or backwards. The physics look the same if time's going backwards or forwards. And if you think about that, the reason that's okay is if we worked out the entropy of this before and after the collision, it doesn't change. You got 2 balls before that are doing whatever they're doing and 2 balls afterwards, and it's the same. So it's fine. But suppose now it was the break. Suppose I filmed the break, and then I played that forwards to you or backwards to you. And I said, hey, Brian, can you tell which of these is actually time going forwards and which ones I've just played you the movie backwards? If it was the break, would you be able to tell?
Pretty easily. And if
Exactly.
I got it wrong and it turned out that the actually all the balls came back into a triangular shape, and then the white ball headed back towards the bottom of the table, I'd go, no, that's backwards.
Exactly.
Right?
Exactly. So that's how our idea of entropy and disorder is intimately related with our perception of time. We're used to seeing things where the disorder increases. That's, the phenomenology of observing the universe evolving.
So, Bill, I'm getting from you that it's very unlikely there's any material that could do whatever this material does in Tenet. But I was thinking about some possibilities. Say, gravity affects time, doesn't it? And, we've spoken about super dense materials, it's like what you might find at a neutron star, where something maybe that's the size of a billiard ball might have a mass of, I don't know, several Earths. Wouldn't if you were able to stand next to this or hold it, which I think is very unlikely, but if you could, would that change time for you relative to people further away?
It definitely would. So it's entirely right what you said. My feeling is I can't imagine how you could, in Tenet, they say they're reversing the flow of entropy of a material. And I can't imagine how you would ever do that. But it is true what you said. Let's be clear, in Tenet then, what that means is that something's going backwards in time. And as you exactly said, it's like 2 things that can occupy the same space-time. One's going forwards and one's going backwards. And I don't know how you could achieve that. However, if you ask, is it possible for different places in space, different objects, different people to perceive the passage of time, or for the passage of time to be different for different people? That entirely is true. That entirely is possible. And as you said yourself, you alluded to, this is all basically Einstein's theories of relativity. And so one of the ways you could do this, you're totally right, is with a large gravitational field. So objects, places in a large gravitational field, the passage of time there is different compared with places with another gravitational field. A simpler one is actually just what's called special relativity, where we look at how time passes for objects moving at different speeds. So this seems like a bit science fiction, but this really is true. So if it turns out that if you have a watch and you try and measure the passage of time, that passage of time that you measure, the amount of time that passes depends on your state of motion. So if you're moving faster than somebody else, in fact, your time, not just your biological perception of time, but actually your time actually goes slower.
If you move at the speed of light, won't time stand still for you? See, I know that in theory, we cannot travel faster than the speed of light. And I think that's because the amount of energy needed to propel any object of mass at faster than the speed of light, there's not enough energy in the cosmos to do that. Is that why?
That's definitely one way of thinking about it, for sure. So, I mean, for worried listeners, we should say that these effects are very demonstrable and measurable, but they only happen at velocities which are close to the speed of light. So, you know, technically speaking, if I'm sitting down and somebody runs past me at 10 meters a second, technically speaking, their passage of time is less than mine, but over 100 meters, that might be by something like, I don't know, 100 picoseconds, or a tiny, tiny amount of time we'll never be able to tell. But as you get closer and closer to the speed of light, Einstein's theory of relativity tells us several things. And one of them certainly is what you said. You can think about the apparent mass of an object, and that increases also, is one way of thinking about it as you get close to the speed of light. So in fact, this idea of what we call time dilation, it actually comes out of the fact which you correctly stated, which the speed of light is a constant. So in everyday life, we're used to just talking about speeds relative to something else. So if you want to think about, you know, how fast I'm moving, and you measure how fast I'm moving, you might want to know, well, am I sat on a bus that's moving at 100 miles an hour? Because how I'm moving then, you know, it's kind of relative to the bus. If I'm sat on the bus, I'm not moving relative to the bus. But if I'm at the bus stop and the bus goes past at 100 miles an hour, I'd go, oh, the bus was moving at 100 miles an hour. Okay. Now, it turns out with light, it just doesn't work like that. If you set up an experiment to measure the speed of light, you will always measure the speed of light, regardless of how fast you're moving. Okay. And it's that fact, the only way that, I mean, that's a fact that's measurable. And the only way that you can understand that fact is by saying that time itself is dependent upon velocity.
Basically, that means if the speed of light is constant, then something else has to give in order for the speed of light to be constant, and it's time.
That's exactly right. So if you think it's weird and you go, oh, that can't be right, the thing is, if you had it the other way around, the speed of light wouldn't be constant, but we can measure the speed of light. And indeed, you know, a huge amount of work was done with the development of relativity, trying to measure the speed of light and trying to understand what is this speed relative to. That was, in fact, the question that kind of started this in a way. If I tell you a speed normally, for example, you might go, oh, well, 5 kilometers an hour relative to what? And in everyday life, that's a perfectly sensible question. But for the speed of light, it just so happens the speed of light's the speed of light's the speed of light. And the only way you can possibly have a situation where you'd measure the same speed of light regardless of your speed is if time gives. So what that means is that time now depends on your velocity. That's really what special relativity, one of the things special relativity says. And this time dilation is a real thing. So it is possible that different people perceive time differently depending on their velocity. That is totally true.
The only way I can see of us going back in time is if we could travel faster than the speed of light, which we can't. But if we could, time would go backwards for us, wouldn't it?
That's perhaps one way you could think about it, yes.
See, we can travel forward in time. If, for example, in Interstellar, that other Christopher Nolan movie, there are a couple of the characters that are close to the black hole, and an hour for them, or less than an hour, they go back to the mothership, and 18 years or 8 years has passed. Well, for them, an hour passed. So that is a way of jumping into the future. You can't go back, but you can go forward into the future. But we can't go back in time unless we travelled faster than the speed of light. I can't see any other way.
Yeah, so I would say that certainly you're right about the forwards jump thing. I mean, don't forget we're travelling in time right now, right? I mean, we're all travelling in time. But if you wanted to basically jump forwards to a place that everyone else hasn't got to yet, as you rightly said, you could accelerate close to the speed of light. So you might have heard your twin paradox. If there were two twins, one gets in a spaceship, zooms off at close to the speed of light, comes back to Earth, that person who's traveled near the speed of light, they will be considerably younger when they get back than their twin is, who basically is on planet Earth. So that again is something which there's plenty of experiments that demonstrate that. In terms of going back in time, I think there are potentially, if you got some some highbrow theorists on, there might be some strange other ways that this is possible, perhaps. Some of the phenomena that we see in quantum mechanics can look like they can be explained by a sort of transactional procedure in which information travels backwards in time. There are other sort of analogies we can make where, for example, a positron, which is an antiparticle to an electron, you might be able to perceive that in a mathematical framework as something which is going backwards in time. But I certainly don't think that we'll ever be in a situation where, we can, you or I can literally travel back to the Stone Age or something.
And I've already done a thought experiment on this one and thought, well, if it was possible to travel back in time, why haven't we had visitors from the future already?
Yeah, that's a great question. That's I've forgotten that's a famous physicist kind of said exactly that, and it became, I can't remember who said it now, but it was that's exactly right. If we can travel back in time, then where are they? And there are people like I think David Deutsch and people like that who, and I think maybe even Stephen Hawking from it, work on what they called chronological protection theories. So they're sort of very worried about the fact that if you could go back in time, that, there'd be lots of things that wouldn't make sense. So the old thing about what if I go back and kill my granddad, that kind of thing, then I wouldn't be alive, so I wouldn't be able to kill my granddad, and those kind of. So there are physicists who've thought about, ways in which you might protect these things from impacting the universe in a strange way. As I said, in the sort of quantum realm, there are people who sort of believe in sort of many worlds interpretations where you might end up in another universe in something that looked like a different time. But in the sort of traditional time travel movies where or like it's trying to say in Tenet that we could have one person who inverts themselves and starts traveling back in time while the rest of us are traveling forward in time. I can't personally see that there's anything in the real world that, as we understand physics at the moment, would be able to do that.
In summary, Bill, there's no tenant in Tenet, but you still enjoyed it.
Yeah, exactly. I mean, sometimes thought experiments are interesting, right? I mean, we know a lot of these worlds that we dream up in, we like to do that as humans, don't we? We like to sit around and go, what if so-and-so? It's just a case, that's why it's cool to talk about these sorts of things with you, because it does often inspire people to say, but could that happen in real life? And then that's an interesting way to sort of relate to, well, what do we know about the way we think the universe works at the moment? And would it be possible or not? But it certainly doesn't stop us sitting around over a beer going, but what if you could do that? That would be kind of interesting. But I think Interstellar, as you said, is probably much closer to the reality of possible time travel than Tenet is.
Thanks for listening to this episode of Sci Fi Sci Fact, hosted by me, Brian Crump, produced by Andrew Robertson, and of course, made possible thanks to the incredible knowledge of those brilliant scientists at the MacDiarmid Institute. You can find more episodes of Sci Fi Sci Fact on the RNZ podcast page, RNZ's podcasts are also available on Apple Podcasts, Google Podcasts, Spotify and iHeartRadio, or pretty much wherever you find your podcasts. And make sure to follow us so you don't miss out on any new episodes.